तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Foundations for concurrency control. In particular, what we did was we looked at the problem of serializability. When transactions are executing concurrently, for example, there are a set of transactions and all these transactions are executing concurrently. We were looking at how this can be interpreted as a serial execution of the transactions. For example, some order in which they could be seen to be executed is what we looked at as a theory for correct execution of the transactions. We also looked at two kinds of serializability. The conflict serializability, where the transactions which are executing on the same data item, when they conflict, how they can be reduced to serializable transactions. That is what we meant by conflict serializability. We also looked at other forms of serializability like view serializability. What we are going to do in this today's class is we are going to look at specific concurrency control protocols, and to begin with, what we are going to do is we are going to look at what are the different types of algorithms that will allow concurrent execution of transactions to be serializable. That means, which produce correct execution of the transactions in a database. So, what we are going to do now is we are going to look at what are the algorithms that we use for achieving serializability, and these algorithms are called concurrency control algorithms. Now, there are two broad classes of these concurrency control algorithms based on how they actually view the system. Some view the system in an optimistic fashion and some view the system in a pessimistic fashion. What we mean by optimistic and pessimistic, I will just explain with a simple example. Now, if you basically look at a narrow pass bridge where vehicles are crossing this bridge, and this is relatively a very low traffic bridge, you do not really look at that vehicles will hit each other when they are passing through this narrow bridge, which in effect means that there are actually vehicles coming from opposite ends. So, you actually assume that relatively the conflicts are very low, which actually means that a scenario where the conflicts are extremely low is one situation. There could be another situation where the conflicts could be extremely high, which means that this is a very high traffic bridge, and hence you assume the possibility of two vehicles finding themselves passing through this narrow bridge at the same time is likely to be high. In either case, what we have to see is these two scenarios are different system configuration. So, what we will do is we will broadly classify conflicts being extremely low and conflicts being extremely high. Now, if you typically look at the way we would see when the conflicts are extremely high is, we basically will put some kind of a traffic signal here and we will ensure only one of the vehicles is into the narrow pass bridge. That means, we in effect will ensure that only one of them is going to be inside. If you do not put the traffic lights here, very often what will happen is two vehicles will get into the bridge and realize they are in conflict and one of them has to backtrack. For example, if you assume that one vehicle V1 has passed up to this point and V2 has passed up to this point and you find there is a conflict here, one of them has to backtrack, and this basically involves lot of hard work, and hence when the conflicts are very high, it is probably not advisable to actually allow the vehicles to get in without any kind of a control. The situation where the conflicts are low is seen to be optimistic. That means, you actually believing that the conflicts are less, which is an optimistic approach, or you view the system in an optimistic way. The second one, where the conflicts are very high, you look at it as pessimistic. Okay. So, this is broadly classified in the two scenarios, optimistic and pessimistic scenarios. Now, what we will do is we will see algorithms that operate on the database system, assuming that the system is in an optimistic scenario, and those algorithms which actually operate assuming that they are in the pessimistic scenario. For example, if you know Chennai, for example, in the Mount Road, if you assume optimistically no vehicles are going to hit each other and remove the traffic lights, everything is going to be chaos there. But on the other hand, if you know IIT Madras, at Gajendra Circle, you are not going to install a traffic light because you do not have that much traffic, it is going to be cumbersome. So, in some sense, if the conflicts are rare and if you apply the other algorithm, it is going to be an overkill. So, typically you have to understand what is the scenario in which the system is in, whether it is in the optimistic scenario or in the pessimistic scenario, and based on that you should be applying these algorithms. Now, broadly what we are going to look at is these two classes of algorithms which are actually categorized, two classes of CC algorithms, but it is possible that there are more algorithms than these two classes. Now, the one class which we are going to look at it is the log based algorithms, which all assume pessimistic scenario, which assume that the transactions are going to conflict with each other often. The other basically are timestamp based algorithms. The timestamp based algorithms assume that the system is in an optimistic fashion and hence conflicts are rare. What we are going to look at is one log based algorithm, the most popular algorithm called the two phase locking algorithm, and we are going to look at a basic timestamping algorithm for the timestamped basic time. For the timestamp based algorithm, we look at the basic timestamp based algorithm. Both these classes will tell us that one belongs to the pessimistic class and the other belongs to the optimistic class. Now, what I am going to do in the rest of this lecture is look at a log based algorithm called the two phase algorithm in detail and explain what are the properties of this two phase algorithm, and we will study this algorithm in detail. And this is the most popular algorithm implemented in practice as well. So, we are going to spend some time looking at two phase locking algorithm used for concurrency control in database systems. As the name suggests, this actually is a locking based algorithm. The lock is very important here, because what we are trying to do here is, when transactions conflict on data items, we are in essential going to allow these transactions to lock the data items. This is equivalent to saying that once the transaction has locked a data item, it is not accessible for other transactions, and in effect that protects the data item from being wrongly manipulated by other transactions. So, locking is a concept that is used in this particular case. Now, to explain the concepts of locking in more detail, we have a problem which we are also familiar in operating systems, called the mutual exclusion problem. What actually the mutual exclusion problem will try to do is, it actually tells that if there is one process P1 which is trying to be in a critical section, the critical section is nothing but a piece of code that is trying to address a shared data structure between P1 and P2. Let us say there is a shared data structure here between P1 and P2, and whenever P1 is in the critical section, it means that it is trying to manipulate the shared data structure here. Okay. Now, only one of them can be allowed to be in the critical section for manipulating. This is basically the read write operations that they might perform on the shared data structure. So, what in essence the mutual exclusion problem does is, it allows only one of the processes to be in the critical section. If one process is in the critical section, it excludes the other process from being in the critical section. This is what we understand in operating systems as a mutual exclusion problem. Now, this is achieved in the operating system by using two operators called the P and the V operators. P is essentially a lock operator. So, when you actually apply a P operation, the process actually uses the P to lock the critical section and uses V to unlock the critical section. This is like, two people cannot be in the room simultaneously, then what they use is, they use a lock, and once somebody acquires this lock, gets into the room, unless he actually unlocks it and comes out of it, the other person cannot enter into the room. That is what actually is prevented by using this P and V operators in the operating system context. Now, in the case of databases, it is slightly different than being just mutual exclusion problem, because what we are actually doing in the database context is, we are actually assuming that there are different types of locks. They could be a read lock, whereas in the case of a mutual exclusion problem, we have only one kind of a lock, but here there are different types of locks that we introduce. Read lock actually says that transaction is trying to read the data item, is trying to read. This is very important. That means, it is not going to write on the data item, it is only going to read the data item. Okay. And if you say there is a write lock, the write lock means that it is trying to write, the transaction wants to write onto the data item. Transaction is trying to write on the data item. Okay. It is also, you can say, read lock. I will abbreviate here afterwards read lock with an RL. An RL shows that the transaction only wants to read the data item, and this is also called a shared lock, because it is possible that a more number of transactions can start reading the item at the same time. It is shared. That means, there will not be any violation if more than one transaction tries to read the same data item, but at any given point of time only one transaction can write on the data item. So, when we abbreviate write lock as WL, this also is called exclusive lock. That means, this lock will be granted only to one transaction, whereas the shared lock can be given to multiple transactions at the same time. This by actually distinguishing the kind of locks, we will in a sense try to increase the concurrency, because whenever a transaction acquires a read lock, it is possible for other transactions also to acquire this lock. But whereas if one transaction is given the write lock, the other transaction cannot be given an extra write lock on the same data item unless the work was finished by the first transaction. So, in other words, as opposed to looking at the operating system context where we have only one lock, we actually distinguish the semantics of the lock here, whether it is a read lock or whether it is a write lock. Based on that, database systems tries to optimize the concurrency that is possible when transactions are simultaneously executing. To also understand the granularity of the lock, this is also important issue when you actually look at locking algorithms. The granularity actually means that how the size of the data items that are locked by the database, by the transaction. Now, it is possible that the transaction only locks a simple data item, which actually means that in a database table, one single data item. For example, in the case of a student record, it is possible that we are locking only the student name, or we are locking the student CGPA. We are not locking any of the other information of the student record. The other one could be the entire tuple. Tuple means all the things relating to the student, one particular student are getting locked, that is called the tuple. This is equivalent to also a row in a database. Okay. The entire row is being locked. The other one is the table, which actually means that now all student records are getting locked. That means that the entire table is getting locked. This is very important to understand the granularity. As you reduce the granularity, the transaction only locks that small item, but if you start increasing the granularity, it starts locking a large number of items. So, consequently, as you increase the granularity of the lock, you correspondingly reduce the concurrency that is available in the system for transactions to execute. One simple example is, for example, if you provide for the entire IIT access at the in gate, where there is going to be a lock, there is going to be only one person entering into the campus at any given point of time, and after he goes out, the lock is given to the next person. It drastically reduces the number of people who can get into the campus at any given point of time. But on the other hand, if the access is controlled at a room level, where when they enter into the IIT, when they reach the particular room, you want only one person to be entering into the room at any given point of time, and that is the point where the room is locked, a particular room is locked, then the amount of concurrency that is available in the system is extremely high. But it depends on where the concurrency is to be provided, but you certainly should lock as small a granularity item as possible, keeping the consistency criteria into account. Now, given the understanding of the lock, let us go on to see how a simple two phase locking protocol will be working in the database context. As the term two phase locking explains, there are two phases in this particular algorithm. The first phase is what we call as the growing phase of the transaction, in which the transaction tries to acquire all the locks, and there is a second phase which is called the shrinking phase, where the transaction tries to release the locks. So, if you basically look at the execution in terms of time, let us say this is the time axis. Now, the transaction starts executing at some point t1, okay, and what it actually does is, as it starts executing, let us say it starts to actually reach execution points where it needs some data items. For example, let us take a simple transaction where it is accessing bank database as shown in the earlier examples. I will basically try to read the balance in a bank account. Now, the first thing that will happen in this case is I try to acquire a read lock on the balance data item, okay, which could mean that I might actually log the entire account of a particular person, and that shows that I in effect reached a point where I have locked, I have asked for a lock. Okay. Now, it is up to the database manager to see that if nobody else has actually has a lock on this at this point of time, or if the other transactions own only the read locks on this data item, I can be granted the lock request. Okay. Now, as I proceed like this, I might keep asking for locks on other items as well. So, this is basically the growing phase where the transaction is actually asking for locks. Okay. This is the first phase of the transaction execution, which is called the growing phase. The growing phase, the transaction is trying to get all the locks it needs to do the work that it has to do. For example, imagine that you have to move some items from one room to the another item, okay, another room. Then you first before moving the items from one room to the other room or manipulating the items in a particular room, you try to acquire locks on all the rooms. That is the first phase of the growing, which is called the growing phase. After you have got all the locks, you do the operation that you are supposed to do, and after that you basically start releasing the locks. This is basically called the shrinking phase. Okay. In the shrinking phase, the transaction is actually releasing the locks. Okay. This is lock acquisition and this is lock release. Okay. In this side, it is basically releasing the locks. Okay. Now, the important condition of two phase locking is once a transaction has released one lock, it cannot ask for any more locks. This is a very important condition and a subtle condition that enforces serializability. We are going to examine this little more deeply a little later, but right now what we understand is the condition between these two phases is once the transaction has reached this point, which is called the lock point. Okay. This is called the lock point. Once the lock point has been reached, let us say at time t, the transaction is not going to ask for any more locks and it only releases the locks. Okay. This we will put it. So, the first phase is the growing phase and the second phase is the shrinking phase. Now, in terms of the two phases, the condition is you are not going to this lock point, you are not going to ask for any more locks after you have reached actually the lock point. This is a very important condition that is enforced. Okay. Now, let us examine how exactly the two phase protocol works for a transaction and understand deeply what are the consequences of applying a two phase locking protocol. Okay. Now, I will take a simple transaction and so what exactly would have happened if I had actually applied a two phase locking algorithm. I will take a simple case of a transaction 1, which is actually reading an item Rx and actually writing an item data item X, and then again it is basically trying to acquire or read an item Y and then write an item Y. Okay. There is basically another transaction T2, which is also doing exactly the same work of reading a data item X, writing a data item X, reading a data item Y and writing a data item Y. Now, if you basically look at how two phase locking protocol would have worked in this particular case, when both these transactions at some point of time come into the system. Now, let us assume that actually T2 has actually come into the system at some point of time. The first thing it will start doing is, as it starts, it requests for a read lock on X, okay, read lock on X. Now, when the read lock on X is granted, it is going to ask for an upgradation of this read lock to a write lock. Okay. Now, it still cannot release this lock on X, though it knows that at this point of time it is actually finished working with X. Now, it is going to work with Y, but still it cannot release the lock on X, because if it has released the lock on X, it cannot ask for the lock on Y. This is the condition of two phase locking. If you have released one lock, you cannot ask for any more locks. So, the transaction T2 will hold the lock X and ask for now read lock on Y, and it will upgrade it to the write lock on Y, and it is at this point of time it will release all the locks. Now, only when it releases the locks on X and Y can the transaction T1 start executing, which actually means that the locking will ensure if T2 has acquired a lock on X, it effectively prevents T1 from acquiring the same lock on X, and hence when there are actually two conflicting transactions on a data item, they will be serialized based on who has acquired the lock first. This is how exactly two phase locking protocol will work. Now, the meaning of acquiring a lock is it subsequently prevents any other transactions from getting the lock on the data item as long as this transaction is using it. This is typically what is achieved as part of the execution. What we are achieving here is what is called conflict serializability. Here in fact, making sure that the transactions execute when they are conflicting on data items in a serializable order. I am going to show a small proof to show that two phase locking in effect produces serializable order of transactions. Before I do that, I am going to look at some more properties of two phase locking in terms of what it can be doing. Since the first thing that is going to happen here is transaction has to wait if the transaction has been locked by some other transaction. If a data item is locked by some other transaction, it is possible that transactions could be waiting for each other. Now, this could result in what we call as the problem of deadlocks. This is one of the problems of two phase locking. What we mean by deadlock is, let us say T1 has actually acquired a lock on data item X, okay, and T2 has actually acquired now a lock on data item Y. It is possible that now requesting a lock on Y and this is requesting a lock on X. Both cannot proceed any further because they have reached this point, but they are not going to release this X or Y till they reach the point of lock point, where this is the lock point. So, both will, they are at this point right now, and there is no way both these transactions can reach their lock point, but unless they reach the lock point, there is no way they are going to release these locks. So, it is possible in which case T1 is actually waiting for T2 to release a lock, and T2 is actually waiting for T1 to release a lock, and both will keep on waiting for each other because they are in a continuous loop here. This in effect means that there is a deadlock, because neither of them will be able to proceed any further, and they will be waiting for each other in this particular context. This is what we mean by deadlocks. This is one of the problems of using a pessimistic kind of an algorithm, because the algorithms which make the system wait for each other will transactions to wait for each other can result in these deadlocks. The deadlocks will basically bring the system performance or the throughput of the system drastically, okay, which means that the system time, the system throughput, the number of transactions that are executed by the system can drastically get affected when there is a deadlock condition. Problem of deadlocks is they need to be detected when they happen, and the system has to recover back from these deadlocks. In this particular case, either of these transactions have to be aborted when a deadlock occurs and make sure they release their lock so that the other transaction can proceed. For example, to break the deadlock, one of the transaction has to be aborted to make sure that T1 can proceed. So, deadlocks needs detection, and subsequently resolving this deadlock required that you abort one of the transactions that is involved in the deadlocks, so that the system can proceed further. This is one of the consequences of two phase locking algorithm. Two phase locking algorithm also does not produce optimal schedules, and we are going to look at the problem of what is an optimal schedule at a later point of time, because the reason for this is it basically ensures, the two phase locking ensures that a transaction always proceeds after it gets acquires locks to the finish. It never grants a lock and later actually aborts the transaction at a later point of time because there is a conflict. Whereas, in the case of optimistic algorithms, it is the other way. They let the algorithm, they let the transactions proceed to execute up till some point of time and resolve the deadlocks by resolve the conflicts at a later point of time by looking at what they have operated upon and seeing at a later point of time if they operate on data items in a conflicting fashion, they will get aborted at a later point of time. So, in that sense optimal schedules may not be possible in the case of two phase locking. We are also going to see a small example and show how time stamping produces optimal schedules compared to two phase locking algorithm. I will explain this concept in a slightly different way by taking what we have actually done in the earlier class of looking at a serialization graph. For example, if you look at as the transactions T1 comes into the system, in effect you are actually creating this graph which shows how the transactions have executed in the system one before the other. For example, in this case let us say there are actually 3 transactions, and then after that basically one more transaction has been executing. Now, we are basically what I am doing here is I am saying that T1 executed before T2, T2 executed before T4. This is required only when there is a conflict. For example, they conflict on a data item X, I need to know how exactly they have executed one before the other. Okay. Otherwise, it does not make, in this particular case T2 and T3 does not have any conflict directly, and hence there is no need for me to actually put a arc here, because they are not operating on common data items. Now, let us say there is an incoming transaction Ti into the system at this point of time. Now, what the two phase locking in effect does is, if there is a lock, for example, let us say there is a Z item on which T3 is actually locked in. Now, the only way Ti can come into the system is only after T3. It can never be, for example, if it is conflicting on this Z data item with respect to any of the existing transactions, the only way you can allow Ti to execute is by being after T3. There is no way this transaction which arrived now after T3 has locked to come before, this is prevented, okay. Which means that the transaction graph, the TG graph here can grow only in the forward direction. That is the only way the two phase locking allows the graph to grow. It does not let the graph to grow in any other direction. But let us understand this problem of this graph growing in other directions as well. This is very interesting for various reasons, because that allows better schedules, optimal schedules to be created when you are actually executing the transactions. Now, to explain this, I will take a simple example of two transactions T1 and T2 executing on two data items X and Y. Now, it is possible that I actually allow the read and the write things to proceed in a slightly different way and ensure that as the transactions are operating on this, either they read a pre copy or a later version which is modified by T1. Now, as we saw earlier, there is a read X and write X that is happening on X, and there is a read y and write y happening on the. Now, let us say T 2 exactly does the other way of reading y, writing y, and then reading x and then writing x. Now, it is possible that when the transaction has actually modified the value of x, you can allow still this transaction to read a pre value, which actually means that it still has not written the value of its modification onto the database. This is the database storage. Since it has not yet modified the value on the database storage, it is possible to allow the T 2 to read a value before modification, which means that there are three possibilities depending on what you allow T 2 to do after T 1 has actually started executing. If you allow the before value, that is pre x, to be read, then the transaction T 2 is actually coming before T 1, because it is actually reading a value that is actually modified or that is not modified by T 1. If you allow T 2 to read a modified value, then in effect it is coming after, that is this is write x, this is after written. T 1 has actually written the value on x, you allow T 2 read the value. Now, two phase locking will not allow the transactions to read pre x, which in effect means that it will prevent this from happening. More advanced algorithms allow the transactions to be placed anywhere in the transaction graph, even they can come before a particular transaction or after the transaction graph. In effect, there is an algorithm called the 5 color protocol, which allows transaction graph to grow in all directions. These are actually 5 different, the 5 colors here denote 5 different kinds of locks, 5 kinds of locks that a transaction can acquire, besides just acquiring a read lock, a write lock. The other kinds of lock which a transaction can be granted when it tries to acquire or read or write data items which were before or after, depending on the pre and post, whether the transactions data items have been modified before or after, it is possible for the transaction to acquire the locks, and this allows the transaction graph to grow in all directions, and this produces more optimal schedules than what we see in the case of two phase locking. The other interesting problem that you see if you actually look at two phase locking is the presence of long lived transactions, which actually means that the transactions are executing for a longer time. For example, the example for a long lived transaction is a transaction that is trying to compute annual interest for every account in the bank. What this does is every year ending time, the savings is taken and the rate interest that needs to be paid for each account is calculated. Now, what this long lived transaction, it runs for a very long time. Normal transactions run only for a few milliseconds, this runs for a few hours, okay, and then it tries to acquire locks on almost all the data items, acquires locks on a large number of data items. Okay. Now, what this means is, this is property 1 and this is property 2, large number of data items. This in effect introduces lot of problems, because this blocks a large number of short transactions. What we actually have is in case short lived transactions. Now, in the presence of long lived transactions, short transactions will have problems of execution, because they do not be able to run, their response time is going to get drastically affected when there are long lived transactions if you apply a two phase locking algorithm, because the long lived transaction will in effect lock all the data items and will not release the locks on other data item till it finishes, because that is one of the conditions of the two phase locking. So, if you apply a two phase locking for long lived transactions which are also there along with short lived transactions, the performance of the short lived transactions will drastically get affected. They will not be able to execute, the response time is going to be really bad when you actually apply two phase locking. This is another very important issue when you actually look at two phase locking algorithm. There are a lot of protocols which modify the two phase locking. There is not strictly two phase locking, they modify the two phase locking condition to actually allow long lived transactions to execute along with short lived transactions, and there is a whole large number of protocols available for making long lived transactions execute along with short lived transactions. We will not go into details of that, but then there is I am going to give references at the end of it pointing out papers which actually give this algorithms, a host of these algorithms. Now, what I am going to now touch upon is the other aspect of how a concurrency control algorithm has to be integrated with a commit protocol. Okay. Now, what we understand by commit protocol and concurrency control algorithm has to be made little more clear. Now, as you can see here, it is only after the transaction commits. If you remember the way we actually explained earlier, that there is the transaction begins execution by actually saying begin transaction. When it actually comes to the end of the transaction, you are actually that is the time when you are writing all the values that the transaction has modified back onto the database. It is till that point the values modified by the transaction are not actually written onto the database. That is what we mean by the commit protocol. There is an interrelationship between concurrency and commit in the sense that as the transaction modifies the values, this is the place where transaction is actually modifying the values. Okay. Transaction modifies, and this is the point only after commit point it is actually visible. The modifications are visible only after this point. So, there is going to be some kind of an interaction between concurrency protocols and the commit protocols, and what we need to understand is how exactly the concurrency control algorithms get integrated with commit protocols, because both together can only provide correctness, and if you basically see that the transaction as it modified it is visible, then it is going to create difficulties in terms of the other transactions reading the values which are not yet committed by the transaction on the database. So, both concurrency and commit protocols have to work together, and we are going to explain in the next few minutes how exactly the commit protocols works along with concurrency control algorithms. What I am going to look at it is how the 2PL algorithm gets integrated with a commit protocol. We are going to look at several ways this can be done with two phase. I will take the simple graph that we have actually taken earlier to see how the commit protocol gets integrated with this. This is a familiar thing that we have actually, now the T1 is the start of the execution of the transaction. This is basically the end of the transaction, and this is the lock point of the transaction. Okay. Now, what we are actually looking at here is, it is possible once the transaction has reached the commit point, it is possible as it is releasing the locks, they are immediately made available for some other transaction. I will take only a simple case of data item X on which the transaction has a write lock. Now, let us say it actually finished and releases the lock, release write lock on X, okay, which actually means that it is possible that this X is available for some other transaction T2 now to actually start working. Now, when T2 actually is trying to now acquire lock on this same data item X, remember that this transaction has still not reached the commit, because the commit point is here. The transaction is actually committing itself here, not before this. So, it actually means that you are allowing the transactions to be executed, transactions to release locks before they actually reach the commit point. This is where the interface between the locking protocols, that is the concurrency control protocols, and the commit protocols come into picture, because the commit protocol starts operating at this point, whereas the before that you have actually applied the concurrency control protocol. Now, if this protocol releases the lock, then the data item is visible for other transactions, because they effectively can acquire the lock, but the value that they are going to read is not the value that actually is produced by this transaction, because it is still not committed. But if it is reading the value produced by, but our understanding is, since it is released the lock, any transaction T2 acquiring the lock is after, and hence there is a relationship between these two, that T1 executed before T2, and hence this is to be preserved, because the value T2 should read is now the value modified by T1. Now, what is going to happen in this case is, if the lock has been released by the transaction before it is actually committed, it is possible at a later point of time at the commit stage, the commit protocol issues an abort, which actually means that this transaction T1 effectively has actually aborted. Okay. Now, this requires that T2 is also actually aborted. This is what we mean by, if you allow the transactions to release the locks before, you basically result in cascading aborts. T1 actually modified a value on X, T2 has actually read this modified value, but now T1 actually aborted for various reasons. Now, T2 should also abort, and this is what really will happen if you apply the transactions to release the locks before they actually committed. Now, a modification to the two phase locking algorithm, taking this into account to avoid cascading aborts, will require that the transactions actually start acquiring the locks. This is actually the lock point, but actually none of them effectively will release their locks till they reach the commit point, which actually means that they keep on holding on to the locks till they reach the commit point, and all the locks are released only after the commit actually happens, which actually means that the transactions commit, that means they write their values, whatever values they have actually got, they will write these values back onto the system, and then they allow or they release all their locks. The locks are not released before committing. Okay. This basically shows that the transaction effectively starts holding the locks till it actually reaches the commit point. This ensures that the concurrency control and the commit protocols work correctly by actually integrating the concurrency control protocols with the commit protocols. Now, what we are going to look at it is all the protocols will require some kind of a modification when we look at how they integrate with the concurrency control protocols. I will show you typically the three properties of, if you remember, for a transaction we are basically looking at three properties of atomicity, which actually ensures that all or none of the actions of the transactions are written. Then we are basically looking at concurrency control. Typically this is consistency, when they are basically operating together, they basically produce consistent results. Then we are actually looking at the property of isolation. Isolation means that one transaction results are not visible for other transaction till the transaction has committed. Then we are talking about durability. This durability is the transaction values are permanently written on the database. So, this together constitutes what we actually called as the acid properties of the transactions. Now, they together have to hold for every transaction. What we are looking at here is basically the concurrency control aspects. Now, they have to get integrated with the isolation properties. This is where the commit protocols are coming into picture. This is where the integration has to take place between concurrency control protocols and the commit protocols. When we discuss the time stamping algorithms also, which operate in a slightly different way of actually ensuring that properties of serializability are actually enforced at the end of the transaction execution, not before. We have to see how that actually integrates with the commit protocols. It is going to be interesting to see how time stamping protocols ensure commit protocols integrate together in a proper way. When we discuss the time stamping algorithms, we are going to look at how commit and concurrency control protocols integrate with each other in that particular context. Typically, the atomicity properties and durability properties are achieved by what we say as recoverability properties, which are actually ensured using the logs. Typically, the logs are maintained to make sure at any point of time the transaction can redo or undo its actions, and that is achieved using the logs. Logs plus the concurrency and commit protocols together ensure that the transaction ACID properties are realized. And to just give you the complete picture, what we basically is looking at, the lowest tier is the database items. These are nothing but the tables that are stored in the database. Now, at the other end is basically the applications which are trying to modify the database items. Now, all the properties algorithms that we are talking about now come in the tier which sits between the applications and the database tables, and this is what we mean by the database management system. Now, in this case the DBMS has various other things. This has to ensure, among other things, a part of the subsystem has to deal with the transactions, and that is basically what we mean by the transaction manager. Now, the transaction manager is part of the DBMS, and this transaction manager is the one which actually ensures that as the applications are executing, the serializability condition is actually enforced using the transaction manager. Now, to give an idea of what exactly happens when a transaction T1 starts executing, when it is actually putting a lock request, let us say it is actually requesting a read lock, this is actually given to the transaction manager. It is up to the transaction manager now to grant this request or disallow this request at this point of time. So, all the transactions in effect will make the request to the transaction manager. The transaction manager, when it locks the data items, for example, there is a table here, the student record table. Now, typically it allows a particular tuple to be locked, then this lock will be granted based on the request that is basically requested by the transactions. So, all the lock requests are coordinated by the transaction manager, and it knows which transaction holds what locks at a given point of time, and ensures that the lock requests are properly coordinated among the various transactions that are executing. It also ensures that along with the for example, if there is a commit protocol that needs to be operated before the lock is released, the transaction manager ensures that the transaction locks are not released till the commit point of the transaction is reached. This is how exactly the concurrency control protocols work in the case of two phase locking. What we are going to do in the next few minutes is sum up and lead to the next set of algorithms, which are typically timestamp based algorithms. Now, what I am going to show you in this particular case is a simple execution of a transaction, and show how two phase locking may not be a best way of executing the transactions and how one can think of in effect producing more optimal way of executing the transactions. This is a very simple example. With this example I will lead to the next set of protocols that I will be talking in the next lecture, which are called the timestamp based protocols. We are in effect looking at the execution of two transactions in T1 and T2. If you typically look at a read x, a write x and a read y and a write y by transaction x and T1 and T2, let us say, just repeats the same kind of execution, you can in effect see that it is possible for T1 and T2 to execute in different possible directions. Now, one way the two phase locking ensures that T1 executes after T2 is both locks of T1, let us say the write lock on x and write lock on y will be granted for T1, which in effect prevents T2 from start executing till T1 has actually finished, which means that the schedule that will be possible in this particular case is read x write x of one, read y write y of the other. This is the point where the transaction would have committed T1 and all the execution of T2 proceeds after this point. But it is possible for, if you carefully notice, what is possible here is this is not the best possible execution of the transactions. It is possible for you to say once T1 has actually finished working on data item 1, data item x, it is possible at that point of time for T2 to start executing on the data item x, because T1 no longer needs that data item on x. Okay. But whole set of problems will come if you let this happen. First thing, as we discussed, we will be sacrificing on the isolation property, because you are letting transaction T2 read the values before T1 has actually committed. So, this will sacrifice the isolation property of the transactions. So, how exactly, if you want to actually optimize the execution of the transactions, probably two phase locking is not the best possible way of executing, but two phase locking is by far the best way of a simple way of executing the transactions. I think we will stop here and going to come back in the next lecture.